The starting point of any design is the thorough understanding of the specifications of the system being designed. In this video, we will focus on the specifications of a typical commercial PV string inverter using high-frequency transformer isolation. In part 1 of the video, we will look at the input-output voltage and power specifications, as well as look at some of the protection features common in most commercial PV inverters. And in part 2, we will look at some of the performance specifications of string inverters. The specifications that we are going to discuss in this video correspond to a 3.8 kilowatt inverter by this PV inverter manufacturer, part1. Now, I must emphasize that these are given only as an example of a typical commercial string inverter, and certainly not to endorse or highlight any particular inverter manufacturer. So the specifications themselves are obtained from the data sheet posted at this website of part1, and obviously these are subject to change. The data sheets were obtained in 2012, and this website, the Solar Design Tool, has the specifications and data sheets of numerous other inverter manufacturers. I believe there are more than about 50 inverter manufacturers specifications, ranging from central utility scale inverters all the way down to micro inverters. And I should also add in the caveat that the following discussions are only my views, only my understanding and inference based on the data sheet, and not from any inspection or testing of the product, or nor is it the viewpoint from the inverter manufacturer. This table, along with the one on the next slide, gives the complete specifications of this product, the 3.8 kilowatt auto rated string inverter. So it covers everything from the input side DC voltage, the output AC voltage, the various protection devices, the efficiency, and the environmental and mechanical specifications, and so on. So in the following slides, we are going to focus on each of the individual sections and look at the corresponding specifications. First, let's look at the specifications of the AC grid to which these string inverters are connected to. Now, this product, similar to any other commercial string inverter, it's capable of being connected to the grid at any of these three different voltage levels. Probably in the US, the most dominant type is the interface at the 240 volts voltage level. Most residences in the US, they are fed by what is known as a split phase 3-wire system. So if you look at the configuration of a typical distribution transformer, so this would be the primary, and on the secondary you have a center tapped secondary. The primary voltage would be 12.47 kV line to line, so that's a common distribution voltage level. So a single phase between a phase and a neutral, so from a line to neutral, so this will be roughly 7.2 kV single phase AC, and that is stepped down. The dot polarities are like this, so that is stepped down to the 120 volts here, another 120 volts here, and this is what comes into the residences. Many of these smaller power loads, they are connected across the 120 volts, trying to balance between the two 120 volts taps, and some of the higher power loads, they are connected directly across the 240 volts. So this is 240 volts. Now, the PV being a fairly high power source relatively, so that is also connected directly across the 240 volts terminal. So this is where the string PV inverters are connected. So when interfaced at the 240 volts level, this product can deliver the full rated power of 3.8 kilowatt. Now, this is actually related to the maximum current rating of the device. So for this inverter, the maximum current is 16 amperes RMS current rating. So the and this is determined by the maximum current rating of the power semiconductor devices, the IGBTs that are used in the inverter. So the product of this current rating 16 IPS RMS and the voltage rating 240 volts is very closely equal to the 3.8 kilowatt, which is the maximum power at 240 volts interface level. Now this product, as I mentioned, can be interfaced at the 208 volts level as well. So 208 is really the line-to-line voltage of a 120 volts system. So V line to neutral is 120 volts, and so V line to line, let's say between VAB. So this would be 120 times square root 3, and that is the 208 volts. Now, because of the lower voltage and with the same current rating, that cannot be exceeded. Therefore, the maximum power that can be delivered at 208 volts interface is less than the 3.8 kilowatts. It is really 3.3 kilowatt, which is just the product of 208 volts RMS and the 16 amperes RMS. Similarly, this product can also be interfaced at the 277 volts voltage level. This corresponds to the line to neutral voltage of a 480 volts three-phase system. So 480 volts is the line to line. Therefore, the V, say phase A to neutral, would be 480 over square root 3, and that is this 277 volts. Now, because of the higher voltage with the same same current rating, we can deliver more power as long as indicated by this note here, as long as there is a sufficient DC power available, and as long as it is exactly at 277 volts, not the lower end of this range, it can deliver up to 4.2 kilowatt power into the grid. Now, in a low frequency transformer isolated string inverter, it is relatively easy to be able to interface at any of these voltage levels, and that is done by simply having different taps in that 60 Hz transformer and using the appropriate tap when it's connected to 240 volts versus 277 or 208. But what we are considering here is a high frequency transformer isolated string inverter, and the grid is directly connected to the DC to AC stage, to a power electronics stage, and the way to support these different voltage levels is by actual control of the DC AC stage. It is also required that the DC link, internal DC link voltage of the inverter is capable of producing an AC voltage that is has a peak value of roughly 304 volts times square root 2. Next, let's look at the range of variation allowed in the grid voltage. So it can vary by between minus 12% of the nominal to plus 10% of the nominal value. So for example, at the 240 volts interface level, it can go down all the way up to 0.88 times 240, which is 211 volts, and all the way up to 240 times 1.1, that is a 10% increase, and that is this 264 volts magnitude. Similarly, at the other two levels, 208 and 277, also we can have a minus 12 to plus 10% variation. If you look at the grid frequency, it is 60 Hz nominal in the US, and the range of variation allowed in the frequency is, for this product, it is 57 to 60.5 Hz. Now the inverter itself is definitely capable of operating at a much wider frequency range. Probably the reason why it is restricted to this range is if you're using a frequency based island detection, then the moment the grid frequency or the system frequency goes lower than 57 or goes higher than 60.5 Hz, then an island is the grid failure is detected, or an island is detected, and the inverter switches off itself. Next, we will look at the specifications on the DC side, on the PV input side. So this particular product has actually two independent MPPT channels. So what that really entails is that this inverter has two DC-DC converters which can be controlled independently to provide maximum power tracking for two separate strings connected to the input of the inverter. Now, each of these channels can handle as much as 3 kilowatt. That is the rating of the DC-DC stage of the inverter. Okay, then there are several DC voltage ratings that are important in the design of the DC to DC stage of the inverter. The first one is this absolute maximum voltage Vmax, which for this product is 520 volts. Now this relates to the maximum number of PV panels that can be connected in series and their combined open circuit voltage. Now we know that the open circuit voltage has a negative temperature coefficient. Therefore the highest voltage occurs at the lowest temperature. So at the lowest expected temperature at a given location, the open circuit voltage of the combined string should not exceed 520 volts for this inverter. Okay, then we have this what is known as a full power MPPT voltage range, which for this inverter is 200 volts to 470 volts. Note the more than 1:2 variation in this voltage range. Now what this means is as long as the well, before that we know that the different makes of PV panels have widely different characteristics in terms of their short circuit current, open circuit voltage, the maximum power point voltage, maximum power point current, and so on. So depending on, or for the given PV configuration and characteristic, as long as the maximum power point voltage happens to be, for that string, happens to be between 200 and 470 volts, then this inverter is will capture the maximum possible power from that string and deliver to the grid, as long as the maximum power is within this power rating of the inverter. Then there is the operating MPPT voltage range, which is a wider range than this full power MPPT range. So what this means is that in this voltage range, the inverter will still try to capture, will try to do an MPPT tracking, but based on the required current and the current rating of the device, it may not be able to deliver the full power that is possible from the sun. The startup voltage V start, that is related to in the morning at what voltage does the inverter begin to operate. It is set nominally 200 volts, but can also be adjusted between 120 volts to 350 volts. So for example, if the number of panels are low, meaning the open circuit voltage is low, then you may set it to as low as 120 volts. But if there are several numbers of a larger number of PV panels connected in series, resulting in higher open circuit voltage, then the startup voltage can be set to a higher voltage level. The reason why it does not start below these voltage levels is that at voltages below this limit, the energy content is so insignificant that it is not worthwhile operating the inverter. Okay, and finally we have this maximum current ratings individually for the two MPPT channels as well as for the entire converter, and we also have this maximum short circuit current limit. Okay, next we come to the protection features of these string inverters. On the DC input side, we have first of all reverse polarity protection, and both on the DC side as well as on the AC side, we have over voltage protection using the varistors. And a key requirement for all PV inverters is to have this ground fault detection to meet the 1741 requirement as well as some of the NEC requirements. And on the output side, another key requirement of any PV inverter is this anti-islanding protection. So this is related to when there's a grid failure, then the inverter should detect this grid failure and de-energize itself within a specified time. And this is done by one of many different types of island detection method, active island detection method. Okay, and finally we have this AC over current protection on the grid side. and for this inverter it is 20 amperes, and this is done by a combination of electronic control of the DC to AC stage, the AC side circuit breaker, and probably using some fuses as well.